Hi folks, today we'll be talking about more properties of invertible matrices, material from 2.2. Let me just recall our setting here. An n by n matrix, A is invertible if, there exists an inverse. So there exists a matrix that we call A inverse such that when I multiply A times A inverse, that's the same as A inverse times A, and that gets me I, the identity matrix IN. Okay, so that was the topic of last lecture, and today we'll talk more about kind of properties of invertible matrices. The first thing I want to point out is kind of if we know that a matrix is invertible, can we say something about related matrices? So suppose A and B are both invertible. Let's say n by n matrices. As I have said before, in the context of invertible matrices, I'm only going to be thinking about square matrices, n by n. Then we have kind of three things happening here. Then A inverse is invertible, so the inverse matrix itself. And what is the inverse of the inverse? It's A. Okay. 2, AB is invertible, so the product of those two matrices, that gives you a new matrix. And what's the inverse of the product? It's the product of the inverses, but in the opposite order, and I'll show you why that is in a second. Last thing is, how does this behave with transposes? So if I take, let me write it this way. So A transpose is invertible. So the matrix I get by transposing is invertible. And what is the inverse? This is easy. It's going to be the transpose of the inverse. Okay? Okay, so I'm actually going to prove number 2. I'll let you look at the book for a proof of all these statements, but let me just show you why. And I think that's probably the most interesting one. Why do you get this kind of reverse order here? Now, I should say that when I'm trying to prove that something's the inverse, right, this is kind of what we saw last time, that if I've given you a candidate for the inverse, it's easy, quote unquote, to check that it's the inverse by just multiplying. So we just, check. So what do? Is I take AB, and then I multiply it by the thing that I'm claiming is the inverse. So the thing that I'm claiming is the inverse of AB is this thing. So I'll multiply it by B inverse A inverse. And now I'm going to use properties of associativity, right? So this is the same as A times B inverse times A. But what is that? So B times B inverse we know is the identity matrix. So I guess I should be a little bit careful. This was actually this, and now we're taking, these times each other. And so now I've got the identity times A. But what's the identity? Whoops, this should be A inverse. What's the identity times A inverse? That's just A inverse, because we know that identity times anything is what you had. And then, this is then the identity because it's A times its inverse. So indeed, this thing is the inverse of, so this implies the inverse of AB is what we claimed, it's B inverse A inverse. Okay, so again, that's the kind of proof of that. I'll let you look at the book for the other two. I want to focus the rest of the time on actually one statement here that says the following. So important fact, I don't know, we'll call it a theorem maybe. So they call it a theorem in the book, I'll call it a theorem. So this says the following, that an n by n matrix, let's say A, is invertible if and only if A is row equivalent, reduces to, is the same way to say this, to the identity matrix IN. Okay? So I should say, maybe just to take a step back, one thing you want to think about is how do you tell if a matrix is invertible? So I should say this provides us a way to, to determine if a given matrix is invertible. all I do is I say I row reduce it, and if it reduces to the identity matrix, which of course is a reduced echelon form, then I know it's invertible. If not, if it reduces to something else with missing pivots, then I know it's not invertible. And we'll see that this actually also gives you a way to actually construct the inverse. So I'll talk about that as well. Okay, so proof, I want to actually go over this proof because it's so important. So this is what's called an if and only if statement, right? It says that this thing, this statement here, being invertible, is equivalent to saying that A is row equivalent to the identity. So what I want to do is there's two parts here. So there's the sort of, this part here, the left implies right. So I'm going to say suppose A is invertible. Okay. Then what I want to show, I want to prove that A reduces to In, which of course, In is this matrix that has ones down the diagonal and zeros everywhere else. Okay. Well, what do we know? So since A is invertible, we know that we know from the previous discussion from last lecture, we know that AX equals B, this equation or this system, has a solution for any vector B in Rn. Okay? So what this is saying is that if I look at this augmented matrix, if I take A as the coefficient matrix and I augment it with B, it'll always have a solution, right? So I don't know what goes here, but I'm going to have pivots everywhere. There's going to be no missing pivots in any row. But now what do we know? That this is an n by n matrix. So this part is n by n here, and I have a pivot in every row, but there's only n columns and n rows. So what this is telling me is that I have, n pivots, one in every row. Okay, but since A is an n by n matrix, this actually means that, this implies that we know what the reduced echelon form is. A has reduced echelon form. I mean, how can I put n pivots in in an n by n matrix? I have to put one there, down the diagonals, and that means that zeros everywhere else. Right? That's the only way to put n pivots in an n by n matrix. And so indeed, this means that A is row equivalent to the identity matrix. I mean, this is the identity matrix, right? Okay, great. So we assumed that it was an invertible matrix, and we concluded that it was a row equivalent to the identity. Okay, what about the other direction? So I'll call this the kind of reverse implication. Now let's suppose A reduces to the identity matrix In. Okay, this is a little bit more complicated, but bear with me here. Well, what we want to prove that there exists an inverse matrix. Right, that's what we're trying to prove, is that we have an inverse matrix. So how would I go about actually constructing that? So what we want is that A times A inverse equals the identity matrix, right? And the identity matrix, again, is this thing here. Okay? Now, remember, how does matrix multiplication work? A times this thing equals the identity. Well, remember that if you take a matrix times another matrix, the columns of what you get are given by, right, taking A times the columns of this guy. So what I'm doing here is A times B1 should equal 1, 0, 0. A times B2 should equal the second column, etc. A times Bn should be the last column, right? Where, what do I mean by here? Where the B1, B2, Bn are the columns of this matrix that I don't know, but that I'm trying to go for, right? So if there was an inverse matrix out there called A inverse, it would have to satisfy this thing. And why is that? Well, because when I take a matrix times another matrix, the resulting matrix has columns given by the first matrix times the columns of the second matrix, okay? So of course these are just the columns of the resulting matrix there. Okay, well, what do we know now? We know that A reduces to, we want to show it's invertible, we know it reduces to in, and hence the system, right, AX equals whatever, I'll call it C, is always consistent. Okay? But look at this. That's what we're trying to solve here, right? These are systems that we're trying to solve. So here's one system where I say A times the thing that we're going for equals 1, 0, 0, 0, right? Here's A times the thing we're going equals 0, 1, 0, 0. So these are just n systems. So in particular, we can solve each of the systems above. You know, what does the system look like? It's A times BI equals this EI vector, right? The standard vector. Okay, and so what the punchline is that we can actually get those vectors. Okay, and so the solutions, the n solutions, give us the columns of A inverse. So we're going to take A inverse is just, you know, those columns that I basically solve, you know, these are solutions to each of those systems. And so we actually got our hands on A inverse. That's what we wanted, right? We wanted to prove that A inverse existed, okay? So we did it. We're done. And we proved that theorem, okay? And again, you know, let me just go back to the statement here that the idea is that a matrix being invertible, a square matrix being invertible is the same as saying that A is row equivalent to identity. That's going to be a very useful fact. Let me point out that this whole argument also gives you a way to compute the inverse, and let me just do that with an example. So note, the last thing I'll say here is note that this procedure also gives a way, provides a way to compute A inverse. And what you do, I'm just going to do this a little bit quickly here, but the idea is I'm going to consider the sort of the super augmented matrix. What I do is I take A over here, and then over here I take the identity matrix. So this is going to be 1, 0, 0, 0, 0, 1, 0, 0, right? So I actually take that matrix here, and I row reduce. And what I'll get is, well, since, you know, well, I row reduce A, and what's going to happen is that if A was invertible, this will change to IN, and then this stuff will come along for the ride, and what will happen is whatever shows up here, this will be A inverse. Because if you think about it, what's going on here is I'm actually solving those n systems that I talked about before, and so what I'm getting is the columns of the A inverse. Okay, and so this follows from what we just did. Maybe just a quick example. If A is 0, 1, 2, 1, 0, 3, 4, minus 3, 8, I consider 0, 1, 2, 1, 0, 3, 4, minus 3, 8. I augment that with the 3 by 3 identity matrix. Okay? And again, what I was saying there is that if you think about it, right, I'm solving that system with the 1, 0, 0 as the left-hand side. I'm also solving this at the same time with the 0, 1, 0. And I'm solving the third one at the same time. So I'm actually solving 3 different systems. When I reduce this thing, this will reduce to 0, 1, 0, 0, 0, 1. And then here you get some, well, fractions, minus 9 half, 7, minus 3 halves, minus 2, 4, minus 1. Okay, so you get some numbers here. You know, I should say that this step is a lot of row reduction, but, you know, you're going to have to pay the price somewhere. And this guy is your inverse, so this will be the A inverse. Okay, and yeah, and so the last thing I want to mention is that if it so happens that you row reduce this thing and you don't get the 3 pivots, right? You don't get the identity matrix here, then you know that it's actually not a invertible matrix. So that's kind of nice, you know, a nice feature of this algorithm, that you can also tell when the matrix is not invertible. So I'll just say the last thing I'll say is that the left-hand side does not reduce to I3, then A is not invertible. Okay? Okay, so that's it for now. We'll continue our discussion of invertible matrices next time.